Hi all, welcome to part 11, module 2, logic system design. So we were discussing the concept of canonical form, right, in the last video, hope you remember, and we discussed something called a sum of product. Sum of product. So what we done there is the particular Boolean algebraic expression we expressed in the form of some set of product terms. Product terms are nothing but which are made out of this AND gate, right? The literals are ANDed together. So that is our product term, and this product term are getting added together to make the Boolean algebraic expression in SOP. Now we are going to see as an equivalent form, but slightly different. That is what is called product of sum. So this is sum of product, and next it is product of sum. So let's make it clear. So the concept is like first once you understand the sum of product, try to link it with the product of sum, so that this will be easy for you. So if you are studying both independently, it will be difficult, and relate and remember the product of sum with respect to sum of product. Okay, so both are standard notations. So equivalently, I think in discrete mathematics, that proportional logic, you might see in something called the product term. There is that conjunction, right? So sum of product means sum is basically the disjunction, so disjunctive normal form, something like that. And product of sum, equivalently we have the conjunctive normal form, because the product is finally we are taking, that is conjunction, and a conjunction of some terms. That is what is happening in conjunctive normal form. Similarly, disjunction of product term, so that is what is happening in distinctive normal form. So that both are same. So if you know that, then it is very easy for you. Otherwise, from here you can link that one. So whatever it is, both are fine. And hope you remember how we come up with the min terms, right? So to write the min term, what we done is, if a variable is value is 0, we represented it in the complemented form. Like here it is 0, 0, 0. So correspondingly x dash, y dash, z dash will be 1. So whenever x, y, z, all of them are 0, this particular term, that is x dash, y dash, z dash, will be 1. That is the meaning of this particular product term. Okay, and you know that, right? So when you are taking complement, these zeros become 1, and you are adding them together. So it 1 and 1 and 1, that will give you 1. So this is something represented by small letter m0, like that. And now similarly, this will be x dash, y dash, z. You don't have to take the complement, because z is 1. So whenever a literal is coming as it is, take the particular variable is having a value 1, take the literal as it is. If the variable is having a value 0, take its complemented form and add them together. So that will make the product term, right? The min terms. Now, so equivalently we have, so this is something we are using in the min terms are used in sum of product expression, where product terms are otherwise the min terms, right? The product terms. Product term. Now, equivalently we have something called product of sum expression, POS, where we are taking the sum terms or the max terms. So max terms are otherwise called sum terms also. Okay. And now you can observe how we are writing the sum term. So when it comes to sum term, it is OR operation, and you know the requirement is like, so when a variable is coming, is having a value 0, here we taken its complement, but here you don't have to take the complement, take the variable as it is. So 0 corresponds to variable as it is, but whenever we are getting 1, it corresponds to the complemented form of the variable. So here it means that this x plus y plus z is giving you 0 when x, y, z are 0. So that is the way we are taking. We will see why it is so. And similarly, in the second case, it is x plus y plus z dash is going to give you 0, right? X plus y plus z dash is going to give you 0 when x is equal to 0, y is equal to 0, and z is equal to 1. That is the meaning. Now, we are focusing on the truth table entries where the function is evaluating a 0. Accordingly, we are writing it. We will see why it is so, okay? And this min terms we are represented, it's a notation actually, it's a small letter m0, m1, etc., where the max terms will be represented like capital M0, M1, like that. Okay, so keep this in mind. And finally, we will focus on all the max term, and that we will multiply together. I mean, we will take the conjunction among them and the operation among them. So that will form the product of sum. Anyways, we will see why we are taking like that. First, we will see the SOP expression, something which you know. So just focus on the function f1 here. So some function I am having, I don't know the function, but I know the truth table of it, right? And what I know is the function is giving me a 1 When the input is like x is equal to 0, y equal to 0, z is equal to 1, here I am getting a 1 for the function. Similarly, here also I am getting a 1 for the function. Here also I am getting a 1 for the function. So when you are focusing on the function f1 alone, so don't look at f2 right now. f2 is a different function. Its implementation is given here. So now we are focusing on f1 only. Okay. So when you are focus on this area, don't look at this lower half. So when I am focusing on function 1, you can see that it is giving me a 1 in 3 cases, right? So that I expressed like this. That means I am getting a 1. See, this one, the first case, this is the first case, right? So this corresponds to the first case. So first case, it is like when x is equal to 0, y equal to 0, z is equal to 1. That means x dash dot y dash dot z is equal to 1. Function is giving me 1. Okay, fine. Similarly, x, so this is the second case. Okay, so how can I write it? X, y dash, z dash, right? So this is my first case. I am getting, this is my second case, right? Now this is my third case. Clear? So what is my third case? X dot y dot z, because all are 1, right? So accordingly, so in any of these 3 cases, I am getting a 1 for the function. So function is 1 in 3 of these cases. So it is actually expressing the function as it is. So in just give any instance like x, y, z, 3 variables are there. I have 8 possibilities, right? 8 instances are possible. So each entry in the truth table I can call as an instance. At a particular moment, what is the value of x, y and z? Now, give any of the combination, you will get the correct value for the function 1. For example, if I am giving, say, x is equal to, I am randomly giving 0, y is equal to 0, z is equal to, say 1, whatever it is. Okay. And I know that in this case, the function is evaluating 0. So just check here. You can see that in this case, this first expression, x dash, y dash, z is going to give me a 1. So this will be evaluated to 1. But these things may be 1 or 0. I don't bother about it, because as I am ORing them together, a single one is enough for me to make the function 1. Okay, hope it is clear. And some other case where the function is 0, you can see that, say, let me take an example where the function is 0. Say x is equal to 0, y is equal to 1 and z is equal to 1. You can see that at this 0, 1, 0 or 0, 1, 1, in all these cases, whatever it is, the function is giving you 0. So you can see that this will be 0, this will be 0, this will be 0. All of them are giving you 0, so that f1 will be 0, 0 or 0 or 0. So like that, this is a correct expression for the function. So and it is standard representation also, that will be, so given any truth table, this is the only one way of representing it, right, in SOP expression. So it is unique and it is standard that everyone can follow. So that is the power of normalization. We are trying some kind of normal form here, some standard form here. Same concept in discrete mathematics, you will focus on the truth table entry where I am having the function is equal to true, and the corresponding values you will do like this. Instead of dot, you will put that symbol, whatever it is you studied there. So that will make the, let me show you. So how the equivalent plus, right? So distinctive normal form look like. Plus is distinction. Distinctive normal form look like. It will be like a x dash and y dash and z. This kind of a notation you might studied, and plus you will represent like distinction, or similarly x and y dash and z dash, or the last term will be x and y and z. This is equivalent distinctive normal form for this f1, right? For this f1, this is equivalent distinctive normal form. Same thing here, dot and plus, like the just notation only differs, and true and false become 1 and 0. That's all. Okay, if you are not familiar with it, right now you are okay, right? SOP is equivalently in proportional logic, this concept is there. Actually, this Boolean algebra, I already told you, we inspire from proportional logic. So everything is here also, but in a slightly different way we are using. Now the important thing is just focus. This is important for you. This many things we already discussed, I just revised only. Now the important thing is, the function is going to give me a 1. See, in these 3 cases, right? Now let me see when the function is giving me a 0. I am just focusing on the entries where the function is giving me a 0. Okay. Now you can see that the remaining 5 combinations are giving me 0. Let me denote them like 1. So I am using different color. This is another case. This is another case. And this is another case, and this is another case. In these 5 cases, you can see that the function is evaluated to 0. Function is giving me a 0, or its complement is giving me a 1. So both are equivalent, right? Function evaluating 0 means its complement is evaluating 1. So what you can see is the function complement, f1 complement is giving me a 1 when f1 is equal to 0. So what are all the cases where f1 is equal to 0? So this is the first case. How can you write it? The first case you can write like x dash y dash z dash. See, this is the first case, x dash y dash z dash. Now this is the second case. See, if I am putting everything it will be confusing. So I hope you can remember this red green color one. Okay, I am representing like this. This is that one, right? Similarly, now this function is giving me a 0. I am focusing on the entries where I am getting a 0. That is x dash, this one I am saying. See, x dash y z dash. X dash y z dash. See, the second entry. X dash y z dash. Similarly, the function is giving me a 0 corresponding to the third entry, that is x dash y z. So this corresponds to the third case where the function is evaluating 0, and this corresponds to fourth case, and this corresponds to fifth case. Let's verify the fifth case, x y z dash. See, x y z dash. Clear? So I can say that in when the function is giving me in any of these 5 cases, you can see that the function is giving me a value of 0. So all them together is giving me a value of 0 for the function in general, or the f1 is giving a 0 means f1 complement is giving f1. Clear? So there is no, the both side of the expression, the LHS as well as RHS is now giving the same meaning, right? So RHS I am getting a 0 in all the 5 cases. LHS, this f1 dash I am focusing. So that is giving me a 0. Otherwise f1 is giving me a 1. Okay. Now see, what I am doing is, this expression is what I am having with me. So just focus on this one. Expression 1. The entire expression I am taking a complement. Expression as a whole I am taking complement means LHS and RHS together you take complement. Okay. So LHS when I take complement, what is f1 complement? The whole complement. F1 complement, the whole complement. Both side I am taking complement. Okay. RHS also I am taking complement. Something like this. So that the value remains same. LHS and RHS both side together. If I have something like A equal to B, I know that A dash is equal to B dash. Both are same, right? Same thing I am doing. So let me erase that part. So when I take complement of that LHS, what I will get? F1 complement, the whole complement will give me F1. Right, now tell me what is complement of this term. So what I am doing is, the first term I am focusing x dash y dash z dash. What is its complement? Right now you know the De Morgan's law. You know that complement, the individual term you take the complement, x1 complement the whole complement and dot become plus, y1 complement the whole complement and dot become plus, z complement the whole complement. This is what you are getting, and equivalently this one is x complement the whole complement is x or y or z. So that is what I am writing here. See this one, this expression. See, this is what is happening, right? Not going to make it complex. Okay, fine. Now it is clear, right? Similarly, for this corresponds to complement of this second expression is what is written here, and the complement of this third expression is what is written here. Complement of the fourth expression is what is written here. I think somebody is missing, right? This is complement of the fourth expression. Which is missing? This is complement of this one, right? Fine. This is complement of x plus y dash plus z dash. Fine. This is complement of, that is x. Okay, sorry. This is complement of this. In between one term is missing. Sorry, I just taken from the textbook only. It was a mistake from the textbook. Or maybe I written, I am not remembering. Sorry for that. One term is missing actually. Okay. Hope you get the mistake, right? Let me add that term. Actually this when you take complement of this you will get this, when you take complement of this you will get this, right? Fine. Now when you take complement of this, that third term complement is missing, that also you have to add. Okay. Now this is actually x dash y x dash, there was a mistake, so let me replace it. So till this is fine. This term is actually a mistake. And you can see that this is the complement of this, x dash y dash z. Now, two more terms instead of this one, there will be two more terms. I have some, I find it difficult to write it over here. So, you know what is complement of this, right? Multiplied with what is complement of this. Okay, hope it is clear. So that you will get 5 terms, that's all. And any doubt you can discuss in the classroom, right? If I am writing it, it will be too complex. So those two terms will also come here. So that was a mistake. And you can see that this x plus y plus z, just look at the previous table, x plus y plus z, that is our first max term. So now we are having max term, that is represented by capital M0. So that is the thing. Okay, and similarly x y dash z, x y dash z, you can see that x y dash z, it is represented by M2. Okay, now you don't have to look at the table, you can simply write it. What you have to do is, you know, just opposite to what we done in case of SOP. So that is why you study one thing and just relate with that one and understand this product of sum. Okay, so x y z, what you have to do is, now it is max term. So the equivalent term, to find out the equivalent term, you know, when it is 0, you are writing the variable as it is. So x y z corresponds to 0 0 0, that is our M0. Now this one, that is x y dash z, this corresponds to 0 1 0, so that corresponds to M2. In between these two terms will be coming, and that was missing there, that is M3 and M5, and finally this will come. So what is this term? This is our M6. Why it is? This corresponds to 1 1 0. So like that you can read it. So that is of my M6. Now you know these are all my max terms or product terms which are multiplied together. That is, I taken the product of max terms. Okay, so this is my product of sum representation, because the max terms are nothing but the sum terms, POS representation, where this is the SOP expression. See, both, hope it is clear, both are clear. So, and you understood the process also, the kind of conversion process. What happened is, the function SOP, we are focusing on the situations where the function is giving me a value of 1, and in POS you have to focus on the situation where the function is giving me a value of 0. Why it is so? When the function is giving me a value of 0, its complement altogether, its complement is giving me a value of 1. Or equivalently, when you take the complement, I am getting the original function. So the right side also you have to take the product complement, and that time the product terms are getting converted to sum terms, equivalent to sum terms. But we are focusing on the rows where I am having a 0 for the function. Right? Now the method is clear for you. So keep that in mind. You don't have to apply all this logic. You can directly write the SOP and POS term simply by looking at the truth table. We will see how it can be done with the help of the truth table now. See the truth table. Look at F2. Okay, truth table of F2. So now we are focusing on F2, and let's see how we are writing it. So this is the SOP expression for F2. Okay, this is the sum of product expression, and this is a product of sum expression. What I am doing is, just look at F2 and look at the entries where F2 is giving me a 1. See, this is the first entry where F2 is giving me a 1. See, and in that case, I've missed on term. So this is the first entry where I am getting F2. I am just focusing on F2, right? You can see this. Don't look at this entry. This is my F1. So this is F2 you have to focus, and correspondingly what is your X, Y, Z. You can see that it is corresponds to the min term X dash Y, Z. See, X dash Y, Z, and it is nothing but M3. Why it is so? Because it is 0, 1, 1. 0, 1, 1 is 3. Okay, min term 3. And similarly, it is giving you a 1 here. Look at this row, and that corresponds to M5, you can see. Look at this row, that corresponds to M6. Look at this row, that corresponds to M7. Cross verify. Now I am removing it. It is looking too much complex diagram. So hope you understand the process, right? So this is the one. And you can represent it in a different way also, equivalently. Sigma, sum of the product terms 3, 5, 6, 7, like that. This is also valid. Right. Now, how to write the product of sum expression? Just look at the row where the function is giving me a 0. You can see that this is the first case where the function is giving me a 0. I am looking at F2, so don't look at this, okay? And now, what is the corresponding sum term? What is the corresponding sum term? It is when x is equal to 0, y equal to 0, z is equal to 0, and the sum term is whether it is x dash or x, you have to take x when x is equal to 0 because it is product term. Okay, I mean, so it is sum term. Just do the opposite thing. So the corresponding sum term or the max term will be x plus y plus z. You can see this, right? Similarly, what is the corresponding max term here? What is the corresponding max term here? What is the corresponding max term here? You will get 4 max term. Okay, so it is equally like min terms are 4, max terms are also 4. And how you can represent this corresponds to 0, 0, 0. So it is max term 0. This is max term 1. I hope it is very clear, right? I am just removing this. Fine. And this you can represent in a different way also, that is product of, that is pi of max terms, that is 0, 1, 2, 4. Now you know it is very easy how you can relate and that this sum term and max term. See in the truth table how many entries are there for you, 0 to 7, totally 3 variable, 8 combinations are possible. And which are all the entries present in the sum term, 3, 5, 6, 7, right? It looks like a complement, right? So all the remaining terms will come in the product term. 0 is not here, 0 will come here, 1 will come here, 2 will come here, 3 is here, so 4 is not here, so 4 will come here, 5, 6, 7 are there, that will not come. So hope it is clear, right? So it is actually complementation only. You can see that here I am taking complement and that logic is actually working. So this is how these two things are there working. But see in the exam they can ask you anything, write the equivalent SOP expression or P of expression. It is very easy, just look at the truth table and you can write. This is one way of doing it. Now let me quickly tell you another way also. I mean sometimes they may give you an expression like this. So here this is my function, okay, this is a function I am having. Now what is the equivalent, one second. Yes, this is a function I am having, and given a function like this, how to write the equivalent product of some expressions? That is the question. See, where is the pen? See. So this is the expression, so just focus on it. Now let me write it here clearly. So xy plus x dash z. This is what I am having. Now how to write the product of some expression? See, by default this expression is in which form? You can see that individual terms are product terms, right, and they are added together. So it is in SOP form. Already it is in SOP. So that is the difficulty we are having. But we just have to convert it in such a way that I don't want product terms here. Here I need sum term and they have to be multiplied together. So you can see that some kind of distributive property you have to apply. Then only you can convert an XOP to POS. Okay, so something, how to make the SOP we already know. One shortcut is like, if you have any confusion, you can directly write the truth table, and from the truth table you can write the POS expression. That is straightforward. But in the exam, if they are asking, they will be expecting this kind of a expression. I don't know. This is the best way to answer it, and it is easy also. Just try to understand it. If nothing is mentioned, you can try the other way also, but still I recommend you to do this. Okay, so what you can do is you just apply the distributive property, and you know how to distribute this plus over dot. Here I will have a dot, right? Systematically one by one you do that. Okay, so what we are going to do is this we are grouping and we are imagining like it is a single term, something like A. Now you know A plus BC, how to distribute, right? Do that. So you know this A treated as a single quantity xy plus x dash into A, you are treating it as single quantity xy plus z. Hope you know this, right? How to do this distributivity part is fine. Still I have this xy, I have to eliminate this also. Now too what I can do is, what I am doing, the same distributivity. See, you know these operators are commutative, associative, distributive, all the things are there. So you can do this in any order. Like you can, here I am distributing plus over dot from left side towards right side. Now I can do the same thing in this direction also. If you have any confusion, what you can do is all are equivalent. You by commutativity you just change the order, like x dash plus xy, and this also you change the order like z plus xy. Okay, then you do in the forward direction, like x dash plus x into x dash plus y. Now it is clear, right? Similarly two terms will come here also. But you don't have to think that much. You can do it in the opposite direction also. Like if you are confused, you do like this. Otherwise, directly do this. That is x dot. I am distributing this way, so that this will be x plus x dash and y plus x dash. Fine. Okay, otherwise do like this, because this x dash plus x is equivalent to x plus x dash also. In any way, all are same, right? So you can see that I'm just removing the steps from here. Okay. Fine. And that is what is shown here. So the first level of distributivity is done, second level of distributivity is done, and you can see that here something is repeating, which is repeating, not repeating. What is x plus x dash? X plus x dash is equivalent to what? By the complement law, it is equivalent to 1. Yeah, or you can see that why it is, because 1 plus 0 is 1, 0 plus 1 is 1, right? It is 1. So this term is 1, that you can ignore. 1 into anything is 1. So only 3 sum terms remain. So now we have the sum of product expression for it. Okay, clear. Yes, that's all. So that about it. So this is the equivalent, not sum of product, sorry, it is what? Product of sum expression for the given function. Actually it was in sum of product form. Now we convert it into product of sum expression. Is it clear? Now there is one more thing I want to add. Still any doubt we will see in the classroom. And I didn't done anything. It's simply we applied distributivity 2 times, that's all. You can do in the way I explained, or right, simply do the distributivity. This xy plus x dash into xy plus z, then x plus x dash into y plus x dash, right? X plus z into y plus z. Hope it is clear, right? Hope there is no doubt. That's all. Now, hope you remember, we have something called a canonical form also. Simply this is sum of product expression, and this is product of sum expression. And when it comes to canonical SOP or canonical POS, just like the principal conjunctive normal form and principal distinctive normal form, here we have a requirement that means each term should contain all the variables. So if you are looking at this here, x variable or its complemented, any one form is fine, is available, y term is available, but z is missing, right? So you have to add that z also, then only it will be in the canonical form. So that canonical form is something unique actually. So this one itself, if you try in a different way, you may be getting slightly different POS also, something. Okay, but when it comes to canonical form, we have the requirement that all the variables should be there. So how can you introduce that z in the first expression? What I am doing is, my first expression is like a x dash plus y, right? With this x dash plus y, if I am adding a 0, is there any change for the value? What I am having is x dash plus y, with that I am adding just a 0. There is no change for the value, right? Now the 0 is nothing but, see, you can, hope you remember this law. Again, from complement law, this is 0. But here in the first expression, which is missing, z is missing. So equivalently, you can write z dot z dash is equal to 0. So what I am doing is, what I have is my first term, that is x dash plus y. It is equivalent to x dash plus y plus 0. When I am adding 0, there is no change for the value. X dash plus y plus the 0 I written like a z dot z dash. There is no change for the value. First term only I am telling, right? Now what you can do? You can apply the distributivity. So this is equivalent to, for the first x dash plus z, you assume like a single variable, okay? And this plus is distributed over this dot. So, sorry, x dash plus y. The first term, this much is single quantity, and that is getting distributed over this particular dot, okay? So plus z. Okay, and that dot will come into between, and the common term, that is x dash plus y plus z dash. Now this is also equivalent, right? So that is how you are getting it. The same way, the second term is x plus z, which is missing, y is missing. So you can add a 0 anywhere. So I am adding a 0 at the end or middle, anywhere you add, and this y is nothing but y plus, sorry, that 0 is nothing but y into y dash. And now distribute, that is x plus z plus y. And it by commutativity, that is nothing but, we write in the order x, y, z. So x plus y plus z, and this will be x plus y dash plus z. Okay, clear. Similarly, this one. Now you can see that each of this sum term is expanded to two sum terms. and totally 6 sum terms will come, but I think again something is repeating 2 times. This, see this one, x dash plus y plus z, x dash plus y plus z, both are same, right? So what you can do is one of the term you can ignore, and other one you retain, because by idempotency x dot x is x only, so keep only one x. So like that, this will come, this will come, this will come, this will come. So I am getting 6, sorry, not 6, one is repeating 5 terms. And equivalently, you know what is this x plus y plus z? X plus y plus z is 0 0 0, it is m0. This is like a 0 1 0, that is 2, m2. And this is like a 1 0 0, that is 4. This is like a what is the corresponding thing? This is like a 1 0 1, that is 5, m5, like that you are getting. That is nothing but the product of the sum terms, that is 0 to 5, another notation. So that's all. Hope it is clear. What we were discussed is like just the product of max term, POS expression. So SOP we discussed in the previous video. First you watch that, then you come to this. It will be very clear to you. And we saw 2 different ways of writing the product of max term or product of sum expression. You can either do this from the truth table, or you can do like this. Okay, and that's all. Thanks for watching.